we see this guy right here. Now, mathematically, this is correct, but in real life, it's not. So when we look at Boolean algebra, let's make this a NAND gate, because that's what I've got. I got 74-4 up here, which is a quad 2 input NAND gate. What Boolean algebra would tell us is that if we call this x, it would say x would equal to, here's my input right here, so this would be a, and then this right here would be not a. Right? You understand? So what that means is it appears that I could never, ever, 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 ever have all highs. So if this was an AND gate, we could change it around. Then Boolean algebra says A and with not A would always equal to a 0. Now in our situation, a NAND with not A should always equal to a 1, right? But that's ignoring what of the inverter right here. What does that ignore? We just got through talking about it. Y'all just gave me the definition just, what, 45 seconds ago. What's that ignoring? The propagation delay. That's saying that that inverter has no propagation delay. But that's not true. So when this guy here switches low, what happens, let's say this guy here has a propagation delay of 10 nanoseconds, which is roughly, that's the generic time we use for a standard gate. Okay, and what I'm using right here, I have a 74 LS, NAND gate. So I have a 74 LS 100. So this 0 right here, as soon as this goes low, then this right here is going to go high, right? You understand? And then 10 nanoseconds later, this right here will go high. Now here's what happens that's interesting, is that when this input right here goes high, it takes 10 nanoseconds for this guy right here to switch. So for that 10 nanoseconds, what does this NAND gate see? Two highs. And what will the output do? It'll go low. And it's not going to be low very long. And then it's going to come up and do here, right? Don't understand. Now this guy here needs to have a propagation delay of less than that right there. So what happens, every time this comes over here and does this, my output would come over here and do this. I didn't give myself enough room. It would do that on every rising edge. Y'all believe me? So what I have set up here, and I've got more than one inverter to get a little bit of propagation delay, is I got this guy right here. So this is a 7400. And then this is a 74 LS 100. or 74LS00. And then this right here is a 7400. So this has no designator. So this is a standard chip right here. And this right here is a 74LS32. This is a NOR gate. And we'll look at the difference. And what I'm doing is I'm applying a digital pulse coming in. And then my other input, I'm sending it through a series of inverters. I think I got 3. It's got to always be an odd number because it's got to give you that inversion. And what we're doing is we're taking the propagation delay and we're ending up with this. Let me move back over to the NAND gate, sorry. So this is the output of my NAND gate. And what's happening is on every rising edge, so let me turn these down. And here's the input signal. So on every rising edge of my input signal, I see a pulse. And this is so fast that if I try to slow it down so you can see the other rising edges, the scope is not going to show it. I mean, it's here. I guarantee you it's right there. But I've got it turned down slow enough that you can't, the scope can't show me that, right? Because it's only there for, a few nanoseconds. But here now it'll start appearing now. So here's my input and here's the output. So on every rising edge, what does this circuit give me? It gives me a pulse, but only on the rising edges. Now, NOR gate works just opposite. So a NOR gate is going to give me a pulse on every falling edge. So here's a NOR gate right here. So here's the falling edge of the clock signal, and I get a watt out of the NOR gate. I get a pulse. Now, if it was an OR gate, it would still give me a pulse, but it would be a high going pulse. And if this was a true AND gate, instead of going low, it would give me a high going pulse. So what I'm saying is that we can use this little circuit, we can use it for what we call an edge detector circuit, which would give me an indication every time I have either a rising edge or I have a falling edge, depending on whether I use ORs or whether I use ANDs. If I use an AND, then I have what we call a falling edge detector, a rising edge detector. See, so this is the pulse output of the circuit. Here's that rising edge. If I use an OR, then here's the output of the OR circuit, and then I get a falling edge detector. Now, why is this important? Well, when I start playing around with clocks, I cannot time off a level. Don't understand that? I cannot time off a level. But if I want something to time, then I'm going to have to time off a what? Off an edge, either a rising edge or a falling edge. So that means just about a lot of your counters have these edge triggered circuits on them. And we'll look at some of those. That's really, but you can't even see it anymore. Why can't you see it? Because I slowed my scope down so you could see the clock, and now this thing here is occurring so fast that we can't even see it anymore. You can't even say, what was that? Right? Ever had that happen where you think you see something? All the time. And there it is. When I turn it up high enough so we can actually see it on the scope, our eyes can see it on the scope, then there it is right there. This is probably Nancy. I gotta talk to her. Yep. Hold on, I gotta talk to her. I'm going to call her. Yeah, I'm going to call.
Oh, okay. Sorry, now say we've been getting calls. Somehow it got on the radio that we're offering training for Mercedes in robotics, and the deadline to join has been extended till April. I don't know anything about it. I've got about 5 calls in there. People's calling wanting to get into the program. And they're saying you're guaranteed a job. And Mercedes don't guarantee jobs. Now you go through their 18-month program. They have a training center down on the Mercedes campus. And if you qualify to it, they take entries once a year. It's an 18-month training program. 18 months. It's free. But you don't get paid a dime. You're not working for Mercedes. If you pass the program, you're put in the employment pool.
In the pool?
In the pool. But in maintenance, it's not one of these guys, and you have to do that to work for Mercedes. You know, there's a lot of people that work at Mercedes. Listen to that when people tell you that. I work at Mercedes. Odds are they don't want. Yeah, if you work for Mercedes, you have to go through that 18-month training program. And then they put you in the pool. Now, if you got accepted now, there would be a high probability that you could get a job because they're trying to up their production. They're trying to double their production down there to $200,000. They said they heard they're building a new plant in, I think, Prattville or something like that. So, I don't know. And that's what, I had to talk to Nancy about that because I don't know what to tell these people. So that's the output of the NOR, and then that's the output of the NAND. Ain't that neat, though? So Boolean algebra tells us that the output would never change. But now that we understand propagation delay, we know it takes time for that 1 and 0 to pass through that what? Through that inverter. So for a very finite amount of time, that output of that gate is going to respond, but it's only going to respond on one of the edges. It's either going to be, it's going to give us an indication when we have a rising edge, or it's going to give us an indication when we have a falling edge. So later on, when we talk about edge trigger, we're not going to look at the circuits anymore. You know that there's not very much to an edge trigger circuit. Very simple circuit. Are you okay? By the way, some of y'all got a reprieve. We lost the whole digital folder off of the server. And guess what was on there? We were able to restore it, but we wasn't able to restore it for this semester. So what that means is that up until this point, all the worksheets that I graded wasn't on there. And, yeah, so the worksheets in this class that we've had up to this point, all those grades were lost. And then, but all the topic quizzes, they're okay. They're in gradebook. Anything that I have to grade outside is gone.
300 for everybody.
Well, it's either way. I won't give hundreds for everybody. I'll just drop it off, which is basically the same thing. Yeah. So the worksheets that we've had up to this point, and the little daily quizzes we had too, they wasn't in gradebook yet. Because the way the daily quizzes would count is they count as one column in the grade book. So I don't really put anything in there until the end of the semester anyway. But my spreadsheet that I was using to keep up with your little quizzes, they're not daily. These quizzes we have at the start of the class, those are gone too. So some of y'all are saying, all right. Somebody else said. So I'm sorry about that. That's life with computers. And I should know better because I know more about computers than the average person or anybody needs to know. So multiplexing, right? Our multiplexers that we're going to use are time domain multiplexers. And then we need to look at demultiplex, and then we're through. Opposite procedure for if I multiplex, I'm going to have to do what? Yeah, but if I multiplex, I'm going to have to do what? Demultiplex. I mean, good gracious, that would be awful. Every one of y'all, when you're using your cell phones, you're multiplexing. But it would be awful if you call somebody and, 10,000 phones rang and everybody picked up and tried to listen to you, right? And everybody was trying to talk and everything at the same time. So how do we demultiplex the phone system? Everybody's assigned to what? A number, yeah, and it's sent out with your packets, sent out on the air with your number and the number that's calling, the number you're going to, and then everybody receives. By the way, everybody receives everybody's phone calls. Y'all know that? So my phone is receiving everybody's phone call that's within this cell right now. So everybody that's in this cell right here, whether it's Verizon or whatever, they all use the same transmit. They all use the same receive frequency. So you're receiving everybody's carrier at this one time.
That's why you can get somebody else on the system.
Well, so if their towers get screwed up, their demultiplex or how they route it, right? You understand, which is really, really interesting.
I mean, you get, like,
We used to get that on hardwired lines all the time. You could hear somebody talking in the background. Yeah. You very seldom hear that on the new digital phones because everything's encrypted. Everything. So you usually, even though your phone's picking it up, your phone shouldn't pass it through. So have you heard that on your cell phone? On a hardwire phone, yeah, a hardwire phone. It used to, we just have signal leakage between the wires, and everything was done analog too. Your house phone system, if you got like I did, I carry a house phone because I found out a long time ago that the Bell system, the phone system runs their own power source. So normally when you lose a cell tower, if you got a wired phone, it still works. I mean, this happened more than once. And plus, you don't have to worry about the bandwidth. They've had problems where when those planes flew into the World Trade Center, nobody could call out. It wasn't because they lost cell towers. What was happening? No, everybody was trying to call at the same time, and they just exceeded the bandwidth of the multiplexers. The multiplexers could only multiplex so many phones, right? And you got 2 million people trying to call everybody at the same time, and the phone system just can't handle that. And yeah, April, and then plus like when Alabama beats Auburn, beats Alabama, they have problems too. So if we're going to multiplex, we're going to have to do what? We're going to have to demultiplex. So we put them together. Sometimes it's the only option we got. I mean, there's no way in the world I could run wires to my cell phone, right? You understand? Or my car radio, or people flying at 35,000 feet up in the air, on an airplane. There's no way in the world we could run wires. We used to get gripes on our airplanes, and we would have a gripe board, and when we come to one, and we'd call down to the maintenance shop and say, we're going to put this work order in service, and the guy in maintenance says, well, you need a fast truck and a long ladder. You know what he was trying to tell us? No, he's telling me the plane was flying. You can't work on a plane when it's up in the air. So they say, oh, that would be pretty good, but we'll get you that fast truck and that long ladder, and you can go out there and fix that sucker. And we did that sometimes too. They would call us down and say, when y'all going to fix so-and-so? And we'd say, well, according to the flight schedule, that thing's in the air. Oh, okay. So this is a 74154. This is a decoder. And we could use a 74138 too. I thought that would probably be the one they would get us to, but this is okay. So we got this E pin. What's E? Enable. Okay. So we got this E pin, and notice they've got the other E pin connected to common all the time, so that one's true. So what we connect up to the E pin up there is we connect the multiplex signal coming in. So this right here is multiplexed. So this would be 16 signals we got right here. So what I would do is over here I have a multiplexer that's bringing in 16 signals. And then over here I got one output. And then what I do on this multiplexer is I use 4 wires to select which signal to put on that output. And then what I do is I take those 4 wires and I send them out with this wire right here. So I'm using 5 wires to send how many signals? 16. They're all multiplexed on that wire. I'm sending 16 signals, but they're not on the wire at the same time. Does that make sense? So what I do when I put zeros on this one, then that would let input 0 come through, and it would come out that line right there. And it would come flying over here. And over here, I would also have a what? 0. We bring those over. So what I'm doing is I'm sending 16 signals, but I'm doing it on 5 wires. Don't understand that. One wire carries all the multiplex signals, and then the other wire is telling the demultiplexer which signal is on the wire. Right? You understand? So this would come on here. And this right here would try to send this to that. Well, how does it do it? Well, when the input signal goes low, this says that enables the chip. This says decode a 0, so output 0 would go low, and all these other ones would be what? They would be highs. When the input goes high, that disables the chip. If we looked at the truth table, if we disable the chip, the output would go high because the chip's disabled. The next time the input goes low, the chip would be enabled, and it would follow that on output 0, output 0. Let's say we're coming over here and we want to send, we're sending signal number 2. So I put this right there. Then that would come over here and put that right there, right? You'll understand. And let's say signal 2 over here looks like this. So I'm coming over there and I'm putting that right there. Well, what would happen is what? Well, when this goes high, when this goes low, it would enable it. And the way the decoder works is that when it's enabled, the selected output goes low because there's the circle. So output 2 would go low. Now what would output 0 be? Now it'd be 1 because it's not being selected anymore, right? Y'all understand? And then when the output goes high, then this guy right here would go high. And we would come up here and generate that guy right there. So whatever's on input 2 of my multiplexer would be rerouted to output 2 on my demultiplexer. But we're sending 16 signals on how many wires? 5 wires. Now how can we send 16 signals on 5 wires? We don't send them at the same time. This is called time domain multiplexing. And what did we just do is just that we saved what? We saved 11 wires. Which don't sound like much, but when you start paying for copper, and then you're doing this all over your plant, right? You understand? Then you save tons of wires. So if this wasn't wireless right here, then what would we have to do? Well, we would have to send these wires all the way back to wherever our server was at. And think about how many computers that are on this campus. Just this campus. And we got this campus and we got Birmingham campus, right? You understand? And we got all these computers, probably 1,000 computers. These are including the people that's using the private network too, right? You understand that? You know, the college has a private network that's open. So if you got a device, you can log into instead of using all your data that you pay for, whichever service that you have. You know, what can you do? You can just log in to Lawson State Wireless and use the wireless instead of using your 3G or 4G or what's the G's out there now? Still 4G? I know they think I got a 4G LT or something.
No, they just came out with
XXLT, yeah. Of course, that don't mean you get it. You just get it on the new phones. But
So how do they go by calculating the gap?
I mean, how do they go about calculating the data? I mean, what do you mean?
Okay, like let's just say you pay for 4 gigabytes.
Okay.
Yeah. How do they go by calculating?
Every bit of data comes over your cell phone counts for your bytes. A byte is how much? How much is a byte? How much is a byte? 8 bits. But you got a minimum frame size is what you do. So you don't ever send 8 bits. The minimum frame size is probably 1024. That's a standard frame size. So 1024 means, and if you probably looked, it jumps. They don't jump in bytes, right? It jumps in groups because they send information is transferred in what we call packets. So you have to be careful there, but so that's why you need to use wireless. If you're heavy into data, which me, I use Wi-Fi all the time because my house has Wi-Fi in it and I have Wi-Fi here and I'm, you know, maybe 5 miles between here and my house. So, and I don't do any data transfer when I'm driving. So, you know, AT&T started that rollover stuff. And, of course, it's only from month to month, but I would never use it. But this is a multiplexer. I can do it with a 74-138, so I can use an 8-to-1 multiplexer, and then a 74-138, which is a 1-to-8 decoder, and that way we can send 8 bits of data on 4 wires. So there this guy here really gives you a advantage because we're sending 16 signals on 5 wires. The other one would be 8 signals on 4 wires. 3 to select and 1 for the data. And then if you go below that, then, you know, it wouldn't be worth your time to multiplex. I mean, if it takes as many wires to multiplex as it does to send the wires, then, you know, so I could send 4 bits of data, but it would take 3 wires. So now our cost is not being that much, right? And if I send 2 bits of data, it'd take 3 wires. So we've lost our. I'm sorry, take 2 wires. So once you drop below that place where what is going to be more cost effective. So the least I've ever seen is 4. I'm sorry, 8, because we can do 8 with 4 wires. But then after that, the savings really jumps up, right? You understand? So I could do 32 bits. Let's see, 4. I could do 32 bits with 10 wires. No, less than that. We could add 1 more wire to get 32 bits. So yeah, we could do 32 bits with 6 wires. So after that, the cost of multiplexing really comes into play, right? So 32 bits with 6 wires, I could do 32, I could do 64 bits with 7 wires. But now you're sacrificing bandwidth, right? Because your wires only got a certain amount of bandwidth it can handle at any one time. So we could get to the point where the wire couldn't support it anymore. And wires have bandwidth because if we send a wire using electricity, we have to send a common. And we usually send them together. And what happens is these wires, if we run them close together, they set up this little thing called a capacitor. And capacitors limit your bandwidth. So when you look at conductors, they're rated at a frequency. This cable, the cable that I passed around, didn't I show you all the twisted pair cable? And it's twisted for a reason, which actually establishes the bandwidth of the cable. So this cable right here is not designed to really handle power. So this is not a power cable, this is a signal cable. And we call it twisted pair. And these twists are very, very important because this determines the bandwidth of the cable. Cat5 cable is around 100 megabits. And I'm not going to explain how we can get a gigabit of information on a cable that's rated at 100 megabits. It can be done. So if you come over here and untwist this cable to make your connections, guess what? What did you just screw up? The bandwidth of the cable. It won't be able to handle 100 megabits anymore without crosstalk and all kind of distortion and everything. Yeah, the maximum you're supposed to unwrap this cable is a half inch. And when you put your connectors on there, that gives you a quarter inch on each side of the connector. So you see people wire these cables up and they'll untwist these things and they'll have them untwisted, 2 inches. And the way Ethernet works is Ethernet is going to try to establish communication. So what it does is it tries the fastest possible, and if it gets too many errors, what does it automatically do? It automatically starts backing down until it communicates. So we have networks out there that's not running at near their rated speed because why? Some guy didn't know how to put on connectors on this cable. They got the twist out too far. So they dropped down to 10 megabits, and they're telling everybody they got a 100 megabit network or gigabit Ethernet, and gigabit Ethernet, you got to really, really, really honor all your twists and everything, and probably move up to like Cat6 cable if you really want. And the category cable determines how many twists you have per inch. And so the more twists you have per inch, the more wire it takes to get those twists, right? So the higher the category of cable you use, the more expensive the cable is. So you have people using Cat3 cable because it's so much cheaper just to save a little money, and then they screw up your network. Your network still works, but it don't do what? It don't run at the speed it should run at. So cable slicing and insulation, not only did we deal with the communication cables and what sets the frequencies and how it works, we also deal with terminating low voltage and also fiber optics. What's nice about fiber optics is it don't have a ground. You don't have to send a ground, right? Because we're sending it with what? Light. So we don't have to worry about EMI. We don't have to worry about twist per inch. We don't have to worry about any of that stuff. And that stuff right there screams.
AT&T Uverse is starting to use it for reserve.
Yeah, they use it in the mines. We first got into it because of the mines. They use fiber a lot in the mines to send information because just about every piece of equipment they got down there runs off electricity. And it generates tons of EMI. And they can't communicate and run and get all the computer feedbacks and everything that they get from those continuous miners and the mining machines and everything. They can't afford to get garbage, so they use a lot of fiber down in the mines. And So we teach how to do that. Currently, we still don't have fiber inside our house, but I guess some houses do if you're Bill Gates.
They brought it into my work.
Huh?
They brought it into my
Yeah, it works. That's fiber too. That orange cable right there. Y'all see the orange cable up there on the switch? This is what we use to connect every computer in this building. That's the main switch for this building right there. And it goes underground over to a building on one cable. Yeah, I don't know. Unplugged. I'll pull it off. So this is demultiplexing. There's not much to it. Books covers and gets into the 74138, but y'all can read that just as good as we can lecture on here. And this is what type of multiplexing. Digital, we use what type of multiplexing? We got two types of multiplexing. We got time domain multiplexing and we got frequency domain multiplexing. Huh?
We use time.
Yeah, digital is time domain multiplexing. As soon as you get into frequency domain, you got to get into an analog world. Because you got to have analog to digital converters, and there's a lot more stuff you got to understand how we modulate the information. Modulate, by the way, is when we take information and we place it on another frequency that we call a carrier. So that's how we modulate it. And what's nice about frequencies is we can have multiple frequencies riding on a cable at the same time. Thank goodness. Because if we couldn't do that, what wouldn't we be able to watch every day? TV, yeah. And that's multiplex. That's frequency domain multiplex. So we have to multiplex and demultiplex with modems, modulator, demodulators. So most of y'all have a cable. You have a cable modem. You make a cable modem in your house, so your computer can get on your cable. Your cable box already has that ability. Your TV already has the ability to demultiplex, right? With that little thing called a tuner. But most everybody, we still have a couple of our TVs that we on basic cable. So the cable just comes directly in, and we can watch, I think, 30 or 40 channels that using basic cable. And then you got your cable box, which is definitely a demultiplexer and a decoder and all kinds of stuff, because that's all that is encrypted. So we okay? So you still send analog and digital information over those cables, and you share it with your network. And if we couldn't multiplex, then none of that would be capable. When we first got into the internet, before anybody could connect to it, you connected through a dial-up. You remember that? Yeah. So we had two phone lines. We had two phone lines in our house. One was for our computer, and one was for our phone system. Until they figured out what to do, people would be on their computer for all the time, and nobody could call them because they couldn't break into their. And if you had call waiting, when that call waiting beep came on, it would disconnect you from American Online, and you'd get beeped, So thank goodness for multiplexing, right?
I thought DSL was pretty cool.
DSL is still around. In fact, U-verse is DSL. It's just a way you can put digital information on the phone system.
Well, they have
It's still basically DSL. I mean, it is. Even though it's just like 4G and 3G they come up with. I don't forgot what they call it now, but if you're on AT&T's U-verse, yeah, it's something. Well, so DSL is still out there, and they still advertise that. The cable company still says, DirecTV, I think, advertises that they're so much faster than DSL. So yeah, U-verse and they do a real good job, but the problem is U-verse is depending on copper wire coming into your house. So DSL is not available everywhere. If they hadn't came in and put high grade copper into your house, then you can't get DSL. So that was real nice, but DSL is still not available. Cable is still not available. There's still a lot of people, believe it or not, that don't even have cables. And we go to DirecTV, right? All right, that's it. So let's go ahead and So this is chapter 8. So when's we have a test coming up. When?
Not in this class. Let's go back and before I give out anything official, let's go back and y'all go to the calendar. I'm having problems breaking out of this thing.